Hi there. In this video, I'd like us to take a look at the atomic structure of materials, or if you like, atomic structure. And in subsequent videos, we'll be looking at metals, polymers, and composites. Okay, but here I'd like to look at the basics of atomic shells, energy shells, occupied by electrons. Um, It's not an exact science, by the way, this, because they're all in a mist of 3D spherical shells. But I want to convey the essence of the basics to you. Okay, we'll end up looking at covalent bonds, but you need some understanding first about shells and subshells before we look at covalent bonds. Okay, so what do we mean by a shell or a main shell? Okay, so we could have perhaps. Here's a nucleus filled with so many protons and neutrons, okay? And classically, what we'd like to do, it's a bit like a dartboard effect. So we have shells like this because they're easy to draw. So shell number n equals 1, n equals 2, n equals 3, etc. And there's more out there, okay? In practice, however, theoretical, should we say, theoretical, in practice, it's not like that at all. It's more of a statistical exercise. So here's the nucleus filled with protons and neutrons, and we don't ever know where an electron is at any one point in time. It could be at any one of these points here. So there's a bit of a mist of possible positions, and then the outer shell there. Again, that's got a whole mist of possible positions about where that electron could be. Well, there are some statistical analyses to help us here, which gives us the simplistic model here. So we can just say, okay, shell 1, 2, 3, 4, etc. And essentially, if an electron, maybe I could call it an electron light blue, like so. So electrons out there, it's going to have a higher energy level than as if it was here. So the higher up you go, the more energy the electron has. Okay. Now then, so what do we do about these actual shells themselves? So we have a shell. We give it a number, n. Okay. And normally we go up to 5 and we then tend to stop because things get a little bit unpredictable and uncertain after this idea of shell number 5. Okay, so we're going to start off with 1, 2, 3, 4, 5, like so. Okay, and what I would like to do is to put in well, a basic algorithm that we use in terms of the maximum number. So maximum number of electrons. We call electrons E, shall we? Maximum electrons is going to be equal to 2 times the n value squared. Okay, so the n value is on the left here. So shell 1, which is over here, that one. We can say, well, 1 squared is 1, 2 ones are 2. If the second shell, so 2 squared gives you 4, 2 fours give you 8. Third shell, 3 squared gives you 9, 2 nines are 18. You see where we're going with this? Okay. Fourth shell, 4 squared gets you 16, 2 16s are 32. And the final one we're going to deal with is the fifth shell. 5 squared is 25, 2 25s 50. So theoretically, that's the maximum number of electrons that can reside in any particular shell. Interestingly, we also have subshells. So subshells, let's bring this back up so you can see these shell numbers there. Okay, subshells. Historically, there tend to be 4. So we have, I'm not going to go through why they've been given these letters, but they just were historically. Okay, SPDF. We like to give them what we call an L number. So L, we're going to say this L number, this shell. So this is moving out, if you like. So in here, we are going to have 1. Here we'll have 2 subshells. Here we'll have 3 subshells, etc. Okay. So the first subshells was S, then P, then D, then F. But to make it a bit more scientific, we use the numbers for L, 0, 1, 2, and 3. And we also have another algorithm here. So the maximum number of electrons in a subshell is actually equal to 2 lots of 2L plus 1. Okay. So we can work out how many electrons are going to be in the S shell. So S is 0, of course, and that's L. So replace L with 0. 2 zeros is nothing. There's 1 in brackets. 2 times 1 gives us 2. Okay. Here our L value for P is 1. So 2 1s are 2, plus 1 is 3. 2 3s are 6. Okay. Here the L value for D is 2. So 2 2s are 4, plus 1 is 5. 2 5s are 10. Okay. And finally, the F shell, L is 3 here. So 2 3s are 6, plus 1 is 7. 2 7s are 14. And you'll notice, of course, that these things are moving up in 4s. Okay. So you start with 2, add 4, add 4, add 4. Right. So now I'm going to get to the nitty-gritty. And I want to talk about the periodic table and some notation that we use, and I would like to mention possibly the first maybe 10 or 11 elements, okay, to show you how the shells in the lower elements are populated. Okay, so I'm going to first of all put some headings in. So I'm going to have a Z number, or the atomic number, which is usually the number of protons in the elements. I'm going to then name the element for you. I'm also going to give you its symbol. And this is the important bit. We're going to indicate the orbital notation. In other words, we're going to describe how many electrons are in the main shells and the subshells. Okay. So maybe I could draw the table first, so I don't want to run out of room. 2, 3, 4, 5, 6, 7, 8, 9, 10, probably room for 11. Okay, so maybe we should change color now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 protons, etc. Okay, I'm going to start with hydrogen. Hydrogen, symbol is H, and well, the Z number gives it away, so we're looking at the number of electrons now, so this is a neutral hydrogen, so we're not talking about an ion in any way. There's no charge, net charge is 0, but we do have one orbiting electron, and that electron predictably sits in shell number 1, which is closest to the nucleus. Then you have to deal with subshells. Well, the first one only has the S shell, and we only have one electron, even though the S shell, as you can see up here, could potentially take up to 2 electrons. Okay, but it's just 1s to the power 1. So all these powers I'm indicating here, here's one, they should be matching this number here, the total, when you add them all up. Okay, right, so now I'm going to move on to the second element in the periodic table, which is helium. Oops, helium, symbol He. This is similar to hydrogen, except rather than one electron in the 1s shell, it has 2. Okay, the maximum allowed is 2 in this subshell anyway. The third element we're going to be looking at is lithium. Those of you know your periodic table, Li. So that one has that inner shell fully populated. Then it has to go, maybe I could leave a gap here. Normally we don't leave a gap, but I'm going to leave one for you, just to indicate that we've moved to a different shell. 2s to the 1. So we're always moving 1, 2, 3, 4, S, P, D, F. Okay, so 2s to the 1, and you look at the powers, the 2 plus the 1 gives you this 3 here. Okay, number 4 is beryllium in the periodic table. Symbol is Be, and this is going to have predictably 1s squared, and then a further 1 in the 2s. Okay, so 2 and 2 gives you 4. The fifth is boron. Symbol is just B for boron. This one is 1s squared, 2s squared. Perhaps you can predict the next one. So it's SPDF. So we're in the second shell. It needs to be P to the 1. Okay, just to remind you. SPDF. Okay. Let's have a look at element number 6, which is carbon. Carbon, capital C, it's 1s squared, 2s squared, 2p, well, add 1 to the previous one, 2p to the 2. 2 plus 2 plus 2 gives us 6. Okay, nitrogen. Nitrogen, symbol capital N, 1s squared, 2s squared, 2p to the 3. Remember, the p subshell can go all the way up to 6 if needed. Okay, so let's move on to 8, which is oxygen. Oxygen, symbol O, and the, as we've called it up here, the orbital notation is 1s squared, 2s squared, 2p This can go up to 6, possibly. 4. 4 plus 2 is 8 for oxygen. Okay. Fluorine is next. Fluorine is the symbol F. We have 1s squared, 2s squared, 2p to the 5, predictably. Okay, 5 plus 2 is 9 for fluorine. Neon, okay, has a atomic number of 10. Symbol is Ne, 1s squared, 2s squared, 2p to the 6. And now this 2p shell is full here on neon. Okay, this one is full. So we need to move up a shell. And this is the last one we're going to look at. I'm not going to go through the whole periodic table for you fall asleep. I'm going to look at sodium. This has the symbol Na. We have 1s squared. Move up a shell, we have 2s squared, 2p to the 6. And then we're going to move up another shell, 3s to the 1. Now then, I want to make something very, very clear here. Put the note over here. Predictable shell population disappears. It doesn't disappear after sodium. It disappears after, I think it's Z equals 20 calcium. Calcium, bitches, symbol Ca. So up to calcium, we can do all of this stuff. After that, we don't have the next outer shell isn't necessarily the one which is populated next. So it all gets very, very complex, higher level things you don't need to know about at this point. What I would like to do now is just finish with a chat about covalent bonds. Covalent bonds. When we say valence, this word valence, we mean the electrons which occupy the outer shells. They're called the valence electrons. I want to use a specific example, something we all know and need, water, which is H2O. And H2O, of course, means 2 hydrogen atoms and 1 oxygen atom. That makes up a molecule of water. So let me finish off here by drawing a molecule. Let me just do an atom first of all. Maybe I could use green here. So in here we have some oxygen. It's actually an oxygen nucleus. And maybe I could draw an O in there. Okay, so that is a letter O representing oxygen in that green nucleus. I'm not going to even draw the 1s subshell here, but what I am going to draw for you, what colour can I use here? Maybe stick with white for now. I'm going to draw as best as I can. This is going to be a 2s subshell for oxygen, and maybe the oxygen, I can give it blue, dark blue. maybe not, doesn't stand out too well. We'll give it light blue electrons. Here we are. So light blue electrons for the oxygen. Okay, so there's the 2s. To draw another orbit here. And this is going to be 2p, of course. It's not a very good join there, but never mind. Now, in the 2p for oxygen, let's just go back up and have a look at that table. So oxygen 2p, here we are, sort of circled it here for you. So in the second shell, it has 6 electrons here. That 2 and that 4 gives us 6. Okay. Well, here's 2 of them here in the 2s. So therefore, 2p must have, change color again. Let's go back to that blue. 2p, they should all be the same size, by the way, these electrons, of course. I'm going to draw a couple here. And possibly put one over here. Okay, so in blue here, we have the 6 electrons which occupy shell number 2 for oxygen. These 2 here, we call a lone pair because they're not going to be associated or bonded through the electron orbits of anything else, for the time being at least. What I'm going to do is, in white, I'm going to draw here a very bad circle. Hopefully this one can be a little bit better for you. You get the idea. Okay, so there's a circle. This thing here is going to be, when I fill it in, it's going to be hydrogen. So this is going to be a couple of hydrogen atoms. Put a H in there. H and a H. Possibly, what colour have I got spare here? Yellow. I'll put the hydrogen's electron in as yellow, shall I? Here. Okay, so that one belongs to the hydrogen. That one belongs to the hydrogen. And can you see possibly what's happened here? Well, let me make a note of this one. So in this one, for hydrogen, the 1s shell of hydrogen appears, this is the important bit, appears filled with 2 electrons. Okay. A standard hydrogen atom, of course, only has 1. However, its 1s shell can accommodate 2. And we have a more stable situation happening when shells are filled, or some sharing goes on and that fills the shells. Okay, finally we look here because this is happening twice. This is here we have the 2p shell or subshell of oxygen appears filled with its maximum of 6 electrons, even though in reality it only has 4. So this is what the sharing does. The sharing sees 2 advantages, and that's why we have lots of bonding between 2 hydrogens and an oxygen, and that's the reason why water is so abundant. Okay, there's a lot more to bonding and large bonding and weak bonds and strong bonds, etc. But this is the essence of it all for you. Hopefully that's been interesting. Thanks for watching, and see you in the next video.